was the nth derivative evaluated at 0 over n factorial. So this was the main result that we achieved yesterday. And we're going to be using this result and some other things to get to the God's existence result. And now again, it's probably worth reviewing for a minute that if you were thinking, oh, well, now I won't be an agnostic any longer, I'll really believe in God and change my ways. This is nothing religious about this. This is mathematical. We're not going to recover everything from yesterday, but it's come to be known as the proof of God's existence for different reasons. But really what we're proving is that I'm going to erase this in a minute, and then we'll have it up again probably 2 minutes before the class ends or something like that. Within the last couple of minutes we'll have this result, that the five most famous numbers in math, 0, the additive identity, 1, the multiplicative identity, pi was probably the next number that you learned was special, and then you learned about the number I last year with Mr. Vermis and Mr. Henry, and then the number E, and that all of these numbers are related in one equation, and this is the equation, and for different reasons this is so remarkable that it's historically known as the formula that proves God's existence. So this is what we're after. So I'm hoping that once we reach this stage, you're not expecting more than that. So that's just going to be it.
Yeah, you will power be negative about it.
So we're going to get here, but it's going to be interesting to see us get here. So I'm going to erase this now because I need some board space to continue, to get going with the presentation. But this is the one to make it clear, especially if you weren't here yesterday, because otherwise we talked about it yesterday if you weren't here, that this is what we're after, but that it's not a destination, it's a journey. Because if all I was just after this, I probably could just, like at this point, based on what we showed yesterday, I could just plow ahead and get there in 10 minutes. But we're going to stop and smell some roses along the way, and so there's some things that we're going to be right near, so why not just appreciate them? So I'm going to be doing some things that probably aren't necessary to get to this point, but we're just right there, and so there's no reason not to enjoy some of the scenery. You stop off at some stops. Oh, let's pull over. What do they call those little spots where you pull over on the highway and
Stops. Shoulder.
never stop there? There's no reason to.
Motel.
I wonder what would happen if I stop here? Throw somebody off a cliff.
Wait, what are we talking about now?
Nothing.
Don't worry about it.
So yesterday we said, oh well, tomorrow, meaning today, we have to develop the similar formula for cosine of x, and then there's another one for e to the x, and ln of x we're going to run into difficulty, but there's a couple of ways around that, and then I think what we ended with was the fact that you don't even really need this formula to come up with cosine of x. I just wanted to remind you about that quickly because we're going to be using that a couple of times today. That there's a topic in our course next year. It's really my favorite topic in next year's course is series. And you're starting to see a little bit about why this is such an intriguing topic. And one of the things that you could do with series is manipulate with a known series to find a new series. So if you want to find cosine of x, you say, well, the derivative of sine is just cosine, so maybe I could just find the derivative of this. So the derivative of x is just 1, and the derivative of x cubed is 3. It comes down, the 3 gets killed with the 3 over the lead 3 of the 3 factorial, so you're just going to end up with an x squared from the power rule, and then over 2 factorial, and then the same kind of thing continues to happen. The 5 comes down from the power rule, and the exponent gets diminished by 1, and the 5 that has become the coefficient gets killed, cancels out, cross-cancels with the lead coefficient off of the 5 factorial, so that becomes a 4 factorial. And so you don't need this Maclaurin's formula to come up with this result, but I think it is going to be important practice for us. So the first new thing of today's lesson is going to be to derive this result, but not the way we just did, not the cute way that we just did, but rather to actually follow that procedure again. The procedure you saw yesterday, I'm going to remind you about it. I guess I'll do it on this board, I guess, but maybe I'll do it on that board actually. So actually, before I do, one reminder, and then again, I'm cognizant of the fact that some people are here for the first time. You learned in previous units, perhaps this year or previous years, that sine was an odd function, and now you know why. And yesterday, I don't know if you mentioned that you learned cosine is an even function, and it should come as no surprise that you have all the even exponents. Something else that's a little interesting, I think I mentioned yesterday that we were doing something like 8 to the 3 made sense to you when you were in 6th grade because it meant 8 times 8 times 8, so that's tangible, that's concrete. But then when you got older, you made sense out of something like that, which previously didn't make any sense, and you made sense out of something like that. And then we talked about, oh, what would that mean? And right now you have no clue what this should mean, but by the end of the lesson you could have a clue and might be able to get a little somewhere with that. But something I think I mentioned yesterday that now is the perfect opportunity to remind you about, because we have this result in front of us. Remember we said yesterday that Mr. Henry and the other guy, they taught you, they had to lie to you. They lie to you for your own good. So you shouldn't get upset with your teachers from last year. But they told you, oh yes, cosine and sine, they never exceed 1. They never get less than -1. They're bounded between 1 and -1. Well, every time Mr. Verma said that to you, he felt a little guilty. Because he knew that in future courses, and not really this course, because you're just going to see a little bit, but that cosine can be bigger than 1. It's if you just don't copy this down at all, but if you wanted to play with this later after we get to the main result, the Euler's formula result, you could do it in a more meaningful way. But if you were to plug I in for x, we had to play around with I a little bit yesterday, so I squared, if you remember, is -1. So it's 1 minus -1, so it's really plus 1 over 2 factorial. And then if you plug I in here, just plugging I into all those spots. So I to the 4th would be, I think, 1, right? And then 1 over 4 factorial. And then 1 over 6 factorial. And then you can end up showing that these terms are small enough that it converges. And do you see any i's in this result?
Nope.
So it turns out that the cosine of I is not only real, because there's no imaginaries, but it's something that's obviously bigger than 1, because it's 1 plus other numbers. 1 plus other positive values. So when you extend the domain of the trigonometric functions to include complex values for the variable, it really does open up doors. So what we're going to do right now is, and this will be necessary for establishing some things, is I want to come up with this formula, but not the cute way. I want to do what we did yesterday in order to come up with this thing. So can I remind you of the procedure that we ended up implementing yesterday? We said, oh, we want to find the cosine of x expansion. I wonder what it is. We secretly know it's up there. Let's say we don't, and we're deriving this. See you later, John.
Oh, no.
He's going to get popcorn.
Excellent.
I know the moment he's waiting for. He's been through this already. He's been around the block on this one. So, gosh, I wonder what the coefficients are. Well, we have a formula there for what the coefficients are. And so the best way to implement that formula is, if you remember, is to try to find a pattern in the derivatives if you can. So this meant the 0th derivative. We're not taking any derivatives at all. So, so the 0th derivative of cosine is just cosine. And now let's see how quickly this pattern emerges. We had a pattern that emerged fairly rapidly when we were trying to find the derivatives and higher order derivatives of the sine function. Let's see what happens here. What's the derivative of cosine? It is negative sine. All right, and then f double prime of x. And what's the derivative of negative sine?
Negative cosine.
Negative cosine is right. All right, we haven't reached that point yet where they started to repeat. See what happens here. What's the derivative of negative cosine?
Sine.
We're still not there, are we? Then we get to the 4th derivative, and what's the derivative of sine? The pattern has emerged. So what was it again? What's that other math idea that had a pattern of 4 aside from the derivatives of sine? I.
The imaginary?
Actually, this result,
Captain.
this synchronization, I to the 0 is just 1. This is what Mr. Henry and Mr. Burmas taught you last year. So I squared is -1, I cubed is -I, and then it just starts to repeat. And the fact that the patterns of the I powers is so in sync with the patterns of the derivatives of sine and cosine, and then the e to the x pattern altogether is like, wow, we're going to see that in a few seconds. And then they just all merge together and come to this big dance at the end that you're going to appreciate very much. So now we're going to use these derivatives in conjunction with that formula, this formula here, for the a sub n coefficients. So let's do that. Let's find the a sub 0 coefficient. A sub 0 should be the 0th derivative evaluated at 0 over 0 factorial. Well, the 0th derivative is just going to be cosine of 0. And cosine of 0 over 0 factorial is just going to be 1. So this guy is just going to be a 1. So cosine of x is just 1 plus some other things that we have yet to determine. Starts off with 1. And you can see what's going to happen here. All of the odd derivatives are going to either be negative sign or sine. Negative sign or sine. So when you play out that formula, it's going to be either negative sine evaluated at 0 over a factorial, or sine evaluated at 0 over the appropriate factorial. So either way, it's either going to be negative 0 or 0. That doesn't matter which one, right? Because you're just going to get 0. So all these even guys are going to, in fact, I may as well just jump to the a sub 3 coefficient just to reinforce that point. So the third derivative evaluated at 0 over 3 factorial ends up being the sine of 0 over 3 factorial. But either way, it's 0. So all of the all of the odd derivatives are going to turn into 0. And so we can just cancel them out here. And so odd coefficient's going to be 0. That odd coefficient's going to be 0. And the evens come out to be what we secretly expect them to come out to be. A sub 2 is going to be the second derivative evaluated at 0 over 2 factorial. That's going to be negative cosine of 0 over 2 factorial. So you can see you're just going to get negative 1 over 2 factorial. So here comes your next term, negative 1 over 2 factorial. And so that times x squared. You can see that that's going to happen for all the even derivatives. You're either going to get negative cosine or cosine in the numerator. So it's either going to be negative cosine of 0 or cosine of 0 in the numerator. Negative 1 or 1. Negative 1 or 1 over the appropriate factorial. Negative 1 or 1. Oop. And so I wanted to go through one of those in full blast. And so we have these two results. You know, if I get a little excited and look for board space and I start to erase this, you have to stop me. But I did make a pedagogical error. I meant to change up colors. It's going to be important for me to do so. So can I change, let's see, how's
Magenta.
how's pink? So I'm gonna write this cosine of x in pink.
But just not purple.
Why purple?
Because it doesn't come out purple.
I'm anticipating something that's going to come a little bit later. I should have done this in a different color. Now we're good. Now I'll use maybe blue for the e to the
Over
x.
there.
All right, so are we ready for e to the x? So we're going to do the e to the x expansion here, but I'm going to need more space later, so I'm going to be erasing this board. I'm going to need these two boards for the main result. So I'll be erasing a couple of boards. This is the only board I can't erase. So in order to be able to do this guy, that's probably a bad color.
One of them.
So in order to do the e to the x
Your head's in the front.
expansion,
Yeah.
we have a little bit of a dilemma. Depending on how many years ago I taught the course, we wouldn't have had this problem, but the curriculum changed a few times over the years, just in minor ways. We tweaked a few things. So we're looking for some expansion like this, an infinite polynomial expansion. Maclaurin expansion, I think we dubbed this yesterday. And if we want to follow that same process that we used over there by Adam and Tom, we have to start finding the derivatives. But what's the problem here?
We don't know.
You know, it hasn't been in our course. Maybe in the middle of some coming attraction, I might have shown you. I don't know. Sometimes I get a little crazy and show you stuff I'm not supposed to show you. The MA police are going to come after me one of these days. So I'm not sure if I did this or not, but it's remarkable. E to the x is the only non-trivial function that has this property. You know, so I guess you can say there's another function that has it, but it's going to be a special form of this really. And so here's your y equals e to the x function, and I'm just going to hand you this. It used to be in our course to do it, but it made sense to save it for, we used to do it, and it took a couple lessons to do it. But next year we're going to learn something called the inverse function theorem, and that's really just a perfect application of the inverse function theorem. It allows you to find derivatives of functions when you know the derivative of the inverse. So the inverse of e to the x, I think you guys know, is ln of x. And a little later we're going to have to review that we're supposed to know the derivative of ln of x. I think hopefully you remember it, but somebody will. Or I'll remind you if I have to. And so since you know the derivative of y equals natural log of x, the derivative of e to the x comes real easily out of that result. So we sort of tweaked the curriculum of HH and took it out. But it's amazing that at any given point, the slope of the tangent line, at any point, I might possibly have mentioned, or maybe somebody knows, probably somebody does know, so I'm not going to call on anybody, because then I just want to look at the expressions on your face when I say it. Did you know that the derivative of e to the x is just e to the x?
Wait, what? You can do that? No way, get out of town!
So if you had it, so let's say this is the point 2 comma e squared, it's like, all right, what's the slope of the line tangent to the graph at 2 comma e squared? And it's like e squared. He says, yes, at 2 comma e squared. What's the slope? E squared. Yes, that's what I'm asking for. It's like one of those Abbott-Costello routines. What's the derivative of e to the x? E to the x. Yes, that's the function I want to know. What's the derivative? E to the x. Yes, well, I'm trying to find out.
Oh no, recursion!
So the derivative, we're handing you here that the derivative of e to the x is e to the x. So we're going to be able to use that fact in conjunction with this formula to come up with a coefficient. So let's see, remember in the case of sine and cosine, we were finding a pattern in the derivatives, and the pattern emerged kind of quickly. Let's hope that the pattern emerges quickly here too. So we'll find the second derivative of e to the x, and it's e to the x. And then we find the third derivative of e to the x, and it's e to the x. You might think that the fourth derivative of e to the x is e to the x, and you'd be right. It's e to the x. And it just keeps being e to the x, so this turns out to be the simplest of all the different expansions, because the derivative is always e to the x. So the case of zero coefficient is the zeroth derivative evaluated at 0 over 0 factorial. And that's just going to be e to the 0 over 0 factorial, but e to the 0 is just 1, so you're just going to get 1 over 0 factorial, so this guy's just going to be a 1. I'll sort of draw a divider line here. Maybe I should use a different color. So e to the x equals 1, plus some other things, and the other things aren't going to be that different. It's not the numerators, so a sub 1 is going to be the first derivative evaluated at 0 over 1 factorial. That's e to the 0 over 1 factorial. You can see what's going to happen. All of these coefficients are going to be whatever derivative, it doesn't matter, it's still going to be e to the 0 in the end, in the numerator, and then divided by whatever factorial you're up to.
No way!
So you're just going to end up with 1 over 2 factorial, 1 over 1 factorial, so this is 1 over 1 factorial plus, and this is x squared over 2 factorial, plus x cubed over 3 factorial. Something that I think I pitched when we were doing infinite series, and we were working with the infinite geometric series and some other series, I think at some stage I had to show you that the harmonic series diverged, and we were able to do that without calculus. This is a famous calculus way to do that. But at some point I think I showed you this one, but this is pretty remarkable. You know, one of the things we're going to be considering next year, sorry, I meant to plug in one, is how quickly series converge. Sometimes a series converges fast. It gets really, really close to the right answer after only a handful of terms. And other times you might need thousands or tens of thousands of terms even to get it to within the nearest tenth of what it converges to. This is a really interesting one. If you plug 1 in here, you're going to get 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, plus 1 over 6 factorial, plus 1 over 7 factorial. Now I want you to notice how quickly those denominators are shrinking. By the time you get to the 15th term, you're in the billions in the denominator, so that the contributions are really, really small. Turns out these contributions are so minimal after the 15th that once you have 15 of these terms, you already have e correct to 20 decimal places. In fact, just think about this. We already have e, look, just from these guys alone, you have it to the nearest tenth. This is, you know, e is 2.7182818459045. Everyone knows that.
Obviously, of course.
If you add up these three guys alone, you already have the 2.5. So you're already almost at the 2.7. And then you add the 1/6, and you're like right there, you're 2.7 to the nearest tenth. So this thing converges in a hurry. And if you just added up the first, on your calculator, the first like 12 of these, you'll see that you get all those digits I was talking about before. So this is a pretty interesting one. I have to write this one down here. E to the x equals 1 plus x squared over 2 factorial, plus x cubed over 3 factorial. And then, you know, you talk about, you know, there's a lot of funny cartoons about these results. was it XCD? Am I saying that right?
XCD.
Yeah, so he's got a really funny one. I'll probably should just post it on the website about the e to the iPi thing. It's hilarious. It really is funny. So I probably will post that to the website. I do want to share it with you guys. I think you'll really be amused. And then there's somebody else that's wrote about an infinite nightmare that he tried to differentiate both sides as many times as he could. So I'll be erasing this in a minute, but let's play the same game that we played here. Remember how we differentiated both sides of this equation? So if you differentiate e to the x, you're just going to get e to the x. So let's see what happens here. So the derivative of just 1 just disappears, right? The derivative of x is just 1. And then the derivative of this guy, the 2 comes down, gets killed with that. And 1 factorial. The derivative here, the 3 comes down, gets killed with the 3. It's like, damn it. 4 comes down, gets killed with the 4 factorial. And it's like, damn, you could do this 10 times for nothing. It's like you just cussed on. I'm doing it until the answer changes. No, I'm in hell. I'm going to do it forever. I'm up to the 18,000th derivative, and I haven't gotten anywhere. So I'm going to erase this because we're going to need the space later. And now there's a real, I need to erase this too, because there's a really interesting one that maybe takes a couple of words. So I'm going to erase this, and then later I'll erase what I replaced it with too, because these are the words I need for the final result. When we get there, we're good on time. So you know how when we were first doing series, I tried to intrigue you about, get you intrigued about how interesting infinite series were by showing you some examples of series which converged to interesting numbers. I think one of the ones I showed you, I really can't stick this into the presentation, but next year is an easy and fascinating thing to show. It's definitely part of one of the top 10 lessons, maybe even top 5, is that if you're looking for pi, it turns out to be 4 times 1 minus 1/3 plus 1/5 minus 1/7. Remarkably easy to come up with this. Don't even need the formulas that we've been playing around with. It's just that this one converges incredibly, really slowly. I might have shown you this one. I think I showed you the e to the one that I just talked about now, just back in January as a fleeting coming attraction thing, to get you into the series and the fact that these things converge and how useful it will be eventually. And then I'm sure one of the things that we did, at least I hope it is, was of course.
Samuel.
Was the harmonic series. And I'm pretty sure that, it's not always the case that I'm able to fool. I try really hard to do a good job trying to fool everybody into thinking that it converges. But wasn't this one of the years? Didn't I get it? Didn't I have everybody?
Yeah.
Who thinks this diverges? No, I think nobody had their hand up. I don't know. Maybe somebody did. Mixing up my years. I know I strive for that in that lesson. Could this be another year where I'm able to successfully fool them into thinking that this converges to something? Because it doesn't look like, it looks like after a certain stage, I think I maybe have fooled you even by writing that down, or I don't know, fooled you, misled you, tried to sucker you into thinking, oh, look how small they are, they can't possibly contribute. But in fact, this adds up to infinity. You could get this to be anything you want. In fact, you could start here and still get it to be infinitely large, and we showed that. That's something that is in our course. Something I might have casually mentioned yesterday, and we're ready to show it now, is that if you alternated every other plus sign with a minus sign, so change that to a minus sign, and change that to a minus sign, change that to a minus sign, etc., then it no longer diverges. You wouldn't say equals infinity. It turns out that this converges to the natural log of 2. You might be saying, well, natural log of 2, where could that possibly be coming from? Well, we're about to show you. So I'm going to erase this now, and we're going to be establishing not this result, but the fact that the alternating harmonic series converges to the natural log of 2. So this is one of those stop and smell the roses along the way. We're right there. We may as well. We're going to encounter a problem right now, though. And maybe somebody can tell me what this problem is going to be. I'm going to try to come up with the expansion for the natural log of x function. I'm going to try to do this, and we're going to encounter difficulties. That is not insurmountable, but I'm hoping you appreciate what the difficulty is before we figure out what to do about it. So what's the problem going to be? We can find derivatives. That's easy enough. It wasn't like the e to the x issue where we didn't know the derivative. Oh, I shouldn't have asked you that one. What is the derivative of L1 of x? I didn't quite write the answer down, so it's possible that maybe somebody doesn't remember, and This is something we're supposed to know from the course, so I'm going to go with my friend Andrew on this.
Down here.
Yeah, we are supposed to know this one. Andrew knows it.
1 over
The derivative
E.
of ln natural log of x is 1 over x. It's actually easier to write it like this. And then this is going to be negative 1, I'll write just in this way, with the powers. Negative, and then the third derivative is going to be 2 times x to the negative 3. So we would have an issue finding derivatives, but the issue will come, when will the issue come up? Who sees what we won't be able to, why we won't be able to finish it off? Hey, John. Rishi, let's hear it.
Should I do f of 0?
Yeah, you will not be able to use this formula to find the coefficients because when we plug 0 into the derivatives, any of the derivatives, you can't plug 0 into any of these guys. Look, you plug 0 in there, or in there, or you've got a problem either which way because they're all undefined. So there are a couple of ways out. One is to go from this formula, which was Maclaurin's formula, to something called the Taylor expansion. And we're going to do that next year. That's the more common way to do it. But the way I'm going to choose to do it is I'm not going to find the expansion for ln of x. I'll just change the problem. We're going to find this instead.
You can do that? Get out of town!
So you're going to help me do this. And now this is one of those where you're going to think you spot the pattern, and you've got to be patient with me. You're going to want me to dot, dot, dot it and jump to the conclusion, but this is a more slowly emerging pattern. You get fooled into thinking it's one thing and it's something else. So I'm going to ask you to be a little patient with me. So what is the derivative of the natural log of x plus 1? What do you think it is? Yeah, it is. I feel a little guilty, though, just saying that without at least mentioning something, because I'll have guilty conscience. So we got a little lucky. I'm going to mention something. I'm going to mention. I had to do that one more time. Had to have an exchange like that one more time before the year was over. So we see next year we're going to learn something called the chain rule. And so if I didn't at least mention this, I'd feel guilty. We just pretended that's a variable. You can't just say because it's true that the derivative of the log of x, the derivative of this is going to be the notation we'll use next year for it, is 1 over x. That is true. But you don't always want to just pretend that x is a variable. Suppose you had this function. You might think, oh, the derivative is just 1 over x cubed plus 5. And it turns out that that doesn't work that way. If you pretend that something's a variable, we're going to learn next year. And finding a derivative, you committed a sin, and so you have to atone for that sin. And the way you atone for the sin is going to be called the chain rule. And the chain rule says if you pretended something's a variable, and you use a derivative rule, and you find the derivative, you only have an intermediate answer, not the final answer. The final answer is obtained by taking what you made believe is a variable and multiplying your intermediate answer by its derivative. So look at this expression that we made believe is a variable. What is the derivative of this thing? 3x. So it turns out this now is right. Now, I could have not mentioned that at all because in this case, tell me why it doesn't matter. If somebody doesn't know the chain rule and somebody just blindly says, oh, the derivative of ln of something is 1 over something. How come I'm right here and I don't have to worry about the chain rule in this case? And if I don't know the chain rule, I'm still getting a correct answer. Jono.
Oh,
The derivative of x plus 1 is just 1.
Yeah, exactly. So when you atone for the sin of pretending that x plus 1 is a variable, you're just multiplying by 1. So I just needed to mention that, or I'd have a little trouble sleeping tonight, tossing and turning. Kathy would be saying, what's wrong? What's wrong? Well, it's today in the lesson. So we're going to find the derivative of this thing here. And I'm a little behind schedule, so is it okay if I turn up the pace just a little bit?
Go.
Just a minute behind schedule. It's okay. If I stop talking about being behind schedule, I'll be back on schedule. So we're going to keep finding derivatives, and so this -2 is going to come down and become a 2. I think. Check me for mistakes. That would be catastrophic if we, had a mistake in the middle of God's existence. Oh no, none of us exist anymore. So now you find this derivative, and I think the -3 comes down. You might want me to write -6, but I'm not. I'm going to write -3 factorial times x plus 1 to the -4. So we're in that situation again where we're taking successive derivatives. And as you take successive derivatives with the power rule, you could see the factorials emerging because these things just kept changing by 1. And so this is going to be -3 times -4, -3 factorial times -4. So I think it's going to be 4 factorial, isn't it? And so what's interesting is that these factorials are going to compete with these factorials. So if something interesting happens, you're going to get the first series. Notice how all of these series involve factorials in their final answer? Well, that's because this formula has factorials in it. So you might think, well, they're all going to have factorials, every single function you ever do. That isn't the case because sometimes when you find the derivatives, the higher order derivatives, you have factorials in the derivatives, and those factorials cancel out with these factorials. So let's watch this happen. I'm going to erase this now. And
Oh my god.
so let's use this. We're using this formula again to find the coefficients for this expansion. So A0 should be the zero derivative evaluated at 0 over 0 factorial. And the zero derivative evaluated at 0 would be the natural log of 0 plus 1. So that's just the natural log of 1, and that's just 0. So this thing's just going to be 0. So the natural log of x plus 1 is just going to start out with a 0 plus other things. I'll just keep the final one down here. Not like 0, the final thing. It's not silly, but it's an intermediate step. Now we try to find the a sub 1 coefficient, and according to that formula right there, that circles Maclaurin's formula for the coefficients, it's the first derivative evaluated at 0 over 1 factorial, which is going to end up being, let's see, what is it? It's going to be 0 plus 1. So the numerator is 0 plus 1, so it's just 1 over 1 factorial. So that's just the 1. So I'm going to stick a 1 here, 1x. And then, again, I ask you to be patient because you might think you've got the pattern right away, but it's a little slow the way this emerges. You find the a sub 2 coefficient using that same formula. The second derivative evaluated at 0 over 2 factorial. And I think that's going to be 0 plus 1 is 1. 1 to the whatever is still 1. And then it's 1 times negative 1. So this is going to end up being negative 1 over 2 factorial. But I'm going to hold off before I write those coefficients because now you think you might have it, and you'll see that you don't have it. You got to be a minute longer. Just about a minute would be enough time, I think.
I think you're awesome.
So the a sub 3 coefficient, just continuing the same procedure. The third derivative evaluated at 0 is going to end up being 0 plus 1 is 1. 1 to the negative 3 is 1. 1 times 2 is 2. So this is 2 over 3 factorial. But the 2 from here will cancel with the 2 from here, and I think you're just going to get 1/3. So one more, I think, will make the pattern. I hope it will. Right here. You find the a sub 4 coefficient, and that should be the fourth derivative evaluated at 0 over 4 factorial. But the fourth derivative evaluated at 0 is 0 plus 1, that's 1. 1 to the negative 4 is still 1. 1 times negative 3 factorial, so negative 3 factorial in the numerator, over 4 factorial. And now I'm hoping that the pattern is clear, that the numerators are factorial. This wasn't really a 2, it was a 2 factorial, this is a 1 factorial. So the numerators are factorial, so are the denominators, but the denominators trump the numerators. So you have one higher value here, so you just end up with negative 1/4, and so you don't have factorials. This thing becomes, just looking at the coefficients, negative, well, I guess I'll do it down here. This is x, and this guy's going to be negative x squared over 2. This guy's going to be, I think, just 1/3 is the coefficient. So plus x cubed over 3, minus x to the 4th over 4, plus dot, dot, dot. So this is a really famous expansion. I don't need to include it on that side for it because it won't be instrumental in improving the final e to the I pi plus 1 equals 0. But if you let x equal 1, you get a very interesting result here. This is what I meant by stopping and sowing the roses along the way. We've done that a couple of times already. You let x equals 1, plug 1 in there. What's going to happen to this thing? What are you finding right now? 1 plus 1, so you're finding the natural log of 2, I think.
Yeah.
So it's the natural log of 2 equals. Now I'm going to take x equals 1 and stick it in there. So let's take 1 and stick the 1 in there, and you're going to get 1 minus 1 squared over 2 plus 1 cubed over 3. Thus, the alternating harmonic series converges to the natural log of 2. Really? I feel a little guilty because
I don't get it.
something we haven't really discussed in this context is interval of convergence, so are you allowed to just even stick the 1 in? We're bypassing that, but you can. And now I think I have just the right amount of time on the clock for
That's all for 5 minutes.
You can't finish that? Is that a challenge?
What? You can do that? Get out of town.
Roll up sleeves.
Oh god.
Are you ready for this?
I'm ready.
No!
I'm really nervous, guys.
I need all I need is this.
I want to video like the rest of the classes like reaction. Yeah.
So really,
Yeah,
our
sure.
best topic next year is going to be infinite series. We spend the longest amount of time on it by far. And we'll revisit all these things and go much, much further. Some of the things I was only able to touch on today, we go into great depth next year. And one of the things is that how many terms do you have to add before you have a certain level of accuracy? Error analysis, we're going to learn a couple of error theorems. You can take a whole course in error analysis, but we'll do a couple of the famous ones. And it turns out that this one also converges pretty quickly, not as quickly as the e to the x one. So if you wanted the natural log of 2 and you were on a desert island, you just add up the first few of these things, first few of these terms, and you actually have the natural log.
Mosquito bite.
All right, what you're about to see, I think will really amaze you. You're going to see how all this stuff comes together along with a lot of the things you learned in your math. The way things often work in math, you do some research on these great mathematicians, and they were just like messing around. It's like, oh, let's try this, let's try that. Oh, I wonder what this could mean. I wonder what that would mean. So they were remember I shoved this in your face and like, oh, well, now you know what this means. It's the cube root of 8. It's 2. We have a value for it. What would that mean? So mathematicians messed around, and Euler was messing around and said, oh, well, I wonder if I just stick an I here, maybe I could make sense out of what e to the I would be. And he ended up with some interesting things, but it didn't lead to the result that we're after. I showed you already what happens when you stick an I in there. At least it's something kind of interesting. But he eventually fiddled around a little bit more, and he decided to make this ix, but I'm going to just make it, I'm going to write the e to the x. Start here, and here comes our final result of what we're after. And if I use yellow there, I want to stick with the same colors. So I'm using yellow for the e, pink for the cosine, and orange for the sine.
Go Cloverfield on this.
So
Panoramic.
e to the x, we know, is 1 plus x
Oh, God.
x squared over 2 factorial plus x cubed over 3 factorial. Now, I know you want me to do a dot, 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 but this one's going to have several patterns, some of which are very slow to emerge. So you have to humor me until I get at least out to the x to the 6th term. And then a dot, dot, dot is appropriate. So now he messed around and said, I think I'm going to just stick in. Well, he tried a bunch of other things first. And he just made that I theta. So that's what I'm going to do. He actually made it ix, but I like I theta for reasons that will become clear in about 5 minutes. So this turns into 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial. And I know you want a dot, 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 but you have to be patient with it because you'll see how there's a lot of patterns. They happen right away, and then some of them are more subtle and they don't happen right away. Plus, you're doing with pluses in yellow, shouldn't you? Plus I theta over 5 factorial, and I need one more.
Final boss.
Eyes in the negative. It's canceled.
So you're already starting to see what's going to unfold, but you don't see all of it. Trust me, you just don't. You will. You'll see.
You ain't seen nothing yet.
So now you start to use the rules for raising I to power. So it's I squared times theta squared, but I squared, in fact, it's on the rear board right behind my good friend Mr. Vermis. And so the I squared is just -1, you know that. And so it's -1 theta squared over 2 factorial. And you keep this going. How about I cubed? What's that again? Yeah, so -I theta cubed over 3 factorial. I to the 4th, just goes back to 1 again. So it's just 1 theta to the 4th over 4 factorial. And then I to the 5th goes back to I again. So you're going to end up with I theta to the 5th over 5 factorial plus I theta to the sixth, but theta to I to the sixth is just going to be -1, isn't it? So -1 theta to the sixth over 6 factorial plus dot, 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 dot. Okay, now you have a few patterns here, and they're all interesting. One of them is real, imaginary. Real, imaginary. Real, imaginary. Real, imaginary. Another pattern. Positive, positive. Negative, negative. Positive, positive. Negative, negative. Well, you really get to appreciate it when you think back to Mr. Vermis. I could remember times that Doug would say, oh, I have this wonderful 10th grade high honors class. You know, I can't believe it. I tell them I want an answer in a certain form. They come up to me and they complain that I took a point off. Mr. Vermis, why did you take a point off? Look, I have 3i plus 7. Isn't that right? Why did you take a point off? He says, well, look at the directions. It's like, put in a plus bi form. Oh, a plus bi form. A plus, why was he so adamant about a plus bi form? Well, let's put this into a plus bi form. So I'm going to put all the real stuff. I'm going to put all the real stuff right here. Real stuff.
It's a major
I'm
orgy.
going to put all the imaginary stuff. I'm going to put all the imaginary stuff right here.
Oh my god. That's right, it's sine cosine.
Right here.
Is it sine
So
cosine?
you're going to help me do it.
I don't know, man. I don't know.
So
I don't know.
let's get all the real stuff. You ready for helping me with all the real stuff? Is that real or imaginary?
Yeah.
Real, let's get here. Real or imaginary? No way. Is going to go here. Shut up. Just all the real things. There's a real term. So kill it. There's a real term, right? Negative theta squared over 2 factorial. Where's the next real term? What? That's not real. That is theta to the 4th over 4 factorial. Where's the next real term? I see it. Negative theta to the 6th over 6 factorial.
Why does that look so familiar?
Just enough. No.
Oh my god.
The imaginaries want their turn. The imaginaries are saying, hey, what about me? So the first imaginary term was here, wasn't it? I put it in already. Where's the next imaginary term?
Oh my god.
I think it's right there. Negative theta cubed over 3 factorial. The I is back to that. It's there. You can go away. There's the next one. 5 factorial.
Wait, I don't get it.
What's going on? Oh my God. These look so familiar. Where have we ever seen this before? And you get this really incredible, famous result. E to the I theta equals, and then it's cosine theta for the expansion for cosine plus I times.
I don't.
What do I do with my hands right now?
And you know all that r cis theta stuff? R e to the I theta is the most famous form. It's just r cis theta is r e to the I theta. So you know
Oh my
I know, I
god.
told you that.
I stopped you from doing that in the past.
Holy pie.
If you put your calculator into r cis theta mode, if you put your, complex mode, you'll get all of your answers will just be in r e to the I theta mode, which is just r cis theta, which is what we've been doing all year, but we just didn't know about it. And now are you ready? Are you ready for the last step?
Plug it in.
Plug it in.
Finish it.
So we don't want this to be generically a theta. What do you wish this were?
Pi.
You wish it were a pi. So let theta
Look, he's going.
go pi.
No.
We're going to get e to the I.
Wait, we don't have time. We don't have time.
And let's see what happens. Oh,
No.
Here comes the hardest part of the lesson by far.
No.
The hardest part of the lesson. What's the cosine of pi? This is really hard. I was like, oh,
Negative
man.
one.
I gotta remember which we couldn't finish the
negative
because people don't know what that is.
Negative one.
Negative one. Here with plus. And then what happens over here?
Zero.
No. You can do both sides. And once. I don't know. Well.
Ah!